Welcome. So let's get into our first mathematical concept of the class, divisibility. So divisibility might sound really cool and something that, or maybe boring because you've already heard of it. We're going to talk about this in terms of the mathematical concept. So we are going to talk about what exactly is divisibility, and we're going to lead that into what is the division algorithm, greatest common divisor, and then something called the Euclidean algorithm. Heads up, the Euclidean algorithm is going to reign supreme in this class, an extended version of that. So, what is divisibility exactly? Well, it may sound really silly and obvious to many of you that a and B, A is divisible by B, or as we write that, B divides A. That's what this little fancy notation right here says. If A equals B times another integer. Now, here's the key reason this is important. We are going to live in integer world. Fractions do not exist. So if fractions don't exist, the actual operation of dividing does not exist. So do not get misled and use division, the division operator, because it really doesn't exist because there's a possibility that it's not defined since we're only in integer world. So we have to be very, very careful. We're going to talk about it's divisible. So not every number is divisible. For example, if I was to say, I can write 3 divides 6 because 3 times 2 is equal to 6. So this is true because 3 times 2 equals 6. However, I cannot say that 3 divides 5 because there is no integer such that 3 times that integer equals 5. At least not in the integers as you know them. We'll talk about modular arithmetic, which will screw all this up, but this is why divisibility is actually kind of important. Now, we actually have a really some cool properties, namely that if A divides B and B divides C, then A divides C. So this is called the transitive property. If A divides B and B divides C, then A divides C. That should be kind of obvious to show that A divides B and B divides A. So in other words, they divide each other. Then they are equal. Now notice again, we're using A, B, and C are in Z. I'm gonna start dropping the let them be integers. I'm just gonna write this notation right here because you should know this at this point in time. If A divides B and A divides C, then A divides B plus C and B minus C. Okay, so all that should be like, I got that. It's not new, it's not fancy. Well, that leads us actually something called the division algorithm. So we start with any two integers, A and B, and we want B to be bigger than 0. That's our only criteria. Then there exists integers Q and R. Not only do they exist, there is unique integers. So that means these are Q. There's not like two Qs. There's only one Q. Oh, it went backwards. Sorry, my apologies. And one R such that A equals BQ plus R. And notice that R, this is, I'm gonna have to draw a line on this part. This is really, really important. R, typo, it should allow equality. Okay, so let me do this real quick. So R can equal 0. So you could have a remainder of 0. So I'll do another example in a second, but if I did something like, let's say A was equal to 12 and B equaled 4, then A equals 4 times 3. So this is the Q plus 0, which is the remainder. And those Q's and R's are going to be important as we kind of move forward. But I just want to hit this idea. So if I'm if my B is 4, all the possible remainders are 0, 1, 2, and 3. All right, hopefully that kind of is getting an idea across. This is something a lot of people often see in discrete, so it's kind of invaluable. So if we want to ask this question of what's the quotient and remainder of 23 when divided by 3, how would you do that? try pausing the video and answering that question. All right. Hopefully you actually paused the video and did it. If not, go ahead and do it now, because I'm going to go ahead and explain just how we do this one. So this one, if we look at 23, one of the things that people sometimes do is they take 23 and they actually do use a division operator, and they do a floor function on that. In other words, when I divide this, I only want an integer to come out. So, or another way to think about it is, what is the biggest multiple of 3 that is less than 23? And that would be 7, because 3 times 7 equals 21. Obviously, if I go with the next one, 3 times 8, that would be 24. That's too big. I got to get rid of it. Well, that means that 23 equals 3 times 7. So again, this is my Q plus some amount. Well, to figure out the remainder, all you got to do is take this, which is 21, and take it away from 23, and that obviously is 2. So this, my R in this case, is 2, and my quotient, or Q, is 7. So that is the idea, and we're going to come back and use this again in a little bit. But to understand why something's going to be really important, let's talk about greatest common divisors. So as long as we're talking about dividing remainders, let's talk about the greatest common divisor. So greatest common divisor, quick reminder, is if I have two integers, A and B, I want to know what's the biggest a common divisor is something that divides both of them, positive. I don't want 0. Well, 0 doesn't divide anything, but I don't want a -1. I just want a positive. Because we then start talking about what is the greatest of these. So among all the possible letters, because obviously 1 divides every integer, but what's the biggest possible integer that divides? And the way we denote that is we say GCD AB. Some books do write just the parentheses AB. We don't really want that. This GCD is way more clear, and it's just more obvious. So we're going to use the GCD notation. Now, if they're both 0, then the greatest common divisor is not defined, because the only, because every number divides 0. So there is no greatest common divisor. It just goes off forever. Kind of annoying. All right, so let's talk about, let's do an example. How would you find the greatest common divisor of 12 and 18? Just pause, and I want you to not just find the greatest common divisor. I want you to think about, how do you do it? Try it. Go ahead and pause the video and find it. All right, so let's come back and do it. The most common technique I see that people do, they do something where they do like, here's 12, and I know that 12 is 3 times 4, which is also 3 times 2 times 2. Another way people do this, sometimes they do 12, and they do a little branching tree, and they go 3, and they go 4. 3 is prime, so I can't do it, but 4 I can break into 2 and 2. And so they get what are called the prime factors of this. So this is one technique that's used for this. If I do 18, I could do 18 is 3 times 6, and 6 also breaks into 2 and 3. And then I would have 18 is equal to 3 times 3 times 2. So no, let's just look at these two lists of things. What are the numbers that they both have in common? Well, they both have a 3 and a 2, and the remaining part, 3 and 2, are not the same. So the greatest common divisor of these two, of 12 and 18, is 6. Now, some of you are like, well, duh. Well, I started with an easy, nice number. Through this cryptography, we don't look on little numbers. We like them for examples to get you started, and then we jump into ginormous numbers. So, for instance, if I just switch it up and go here, now I want you to find the greatest common divisor. You can use that technique. You can switch it up and do whatever you want. I want to pause the video and try to find the greatest common divisor of these two. Go. All right. So let's say you did that. Again, There's a lot of different techniques we can do. So let's try that whole tree technique again, where we just have 748 over here and 2024 over here. And we're going to break them up. And the best way to do this actually is to just break them by whatever you know goes into them. Well, they're both obviously even numbers. So this one would be a 2, and that'd be 374. And this is a 2 and 1012. And I'm looking at this and I'm like, hey, I can take a 2 out of this one again. And you keep going on this process until we get to a certain spot. So if you did the tree, you'd end up with something like this, which simply tells us that, again, that 748 equals 2 times 2 times 11 times 17, and 2024 equals 3 2s. So I'm going to go 2, 2, 2, 11, and 23. And now I'm just looking for what they have in common. Well, they both have 2s, and this has 2 2s. So I'm going to take 2 2s from over here. And then what's left is I have a 11 over here and 11 over here. So the greatest common divisor of these things equals 2 times 2 times 11, or in other words, 44. So this is how we can find the greatest common divisor. However, it is highly inefficient. And even for a problem like this, requires a lot of trial and error. I'm going to guess that many of you, if you did this, you got to like 187, you're like, well, how do I do that? And you're just checking numbers at that point in time. There's some things we can check because we know that we only have to check up the prime numbers up to the square of this. But again, prime numbers are hard to find, which is part of what current cryptography is based on. So finding if a number is prime is actually exceptionally hard and part of our challenge of this class. And we'll come back to that again. But is there a better way to do this? And the answer is yes. And it involves something called the Euclidean algorithm. Now, this is an algorithm. I'm going to walk you through the steps, help you understand the basics of it, and then we're going to do some examples. So we start by setting R0 and R1. So this is a recursive function. It's going to repeat through its steps until it reaches a certain kickout point, number 4 and 5. And so we're going to start. We set I equaled 1. Then Ri minus 1, which obviously is R0. I'm going to divide that by this to get the quotient. So notice I'm using the division algorithm right here, using my first number. So this in essence would be A equals B times some Q1 times R, and we'll call it R2 because we're starting this with a thing. Now, what we then do from there is it says if, where this remainder obviously has to be in the normal bounds and so forth. If this remainder right here, sorry, that should be a plus. It's a error typo. If that's a plus, this thing has, if it's 0, then the truth is that the previous thing, in this case B, is the greatest common divisor because obviously it goes into both them. We're good. If it's not 0, then what we do is we repeat the steps, but we now take the B and it becomes this, and I'm saying it's R2 times some new quotient plus some new remainder. So I'm going to run the division algorithm again, and I'm going to figure out the remainder. If this remainder is 0, then it means that R2 is the greatest common divisor. If it's not 0, I just have to run through it again. And to see this more clearly, let me just run through an example. So I want to find the greatest common divisor of these two numbers. So I take the biggest one, 969, well, that's going to change. That's just a typo. But I mistyped it. This should be 963. My apologies. That was just a typo. So it should be 963 right there. Equals 600. I didn't notice until it was on the big screen. 651 times 1, because that's plus this. So this is my this is remainder 2. Now what I'm going to do, because remainder 2 is clearly not 0, is I'm going to execute it again, except this time I'm going to have 657 is going to come over here. I'm going to say how many times does 306 go into it, and I get a new remainder here, which is R3. R3 is clearly not 0, so we execute the process again. So we get the 306 equals 45. How many times with what remainder? Well, it's 36. Still not 0. Execute it again. 46 slides over. 36 times 1 plus 9. Still not 0. We do it one more time. And boom, we have a remainder that is 0, which actually means that 9 is the greatest common divisor of these particular things. So this is the process that we use to go through this over and over and over again. And this is the idea that you need to practice. I'm going to give you some practice problems to try doing it. And then I'm going to ask an interesting question. Can we go backwards? And this is a fun question. Can I go backwards so I can write that 963 times some number, we'll call it J, plus 657 times some number K is equal to 9? Can I do that? And the answer is you can. And we'll come back, we'll talk about that more, but that's part of your question now to answer in the discussion board.